Thank you very much for having me. And I'm Michele Barbato. I'm a professor of structural engineering and structural mechanics at UC Davis, also director of the UC Davis Climate uh, Adaptation Research Center and the director of the Climate Initiative within the Citrus and Banatao Institute, which is a research center that goes across 4 campuses of the UC system, UC Berkeley, UC Davis, UC Merced, and UC Santa Cruz. As from what I said before, my expertise is in structural engineering, structural analysis, and analysis of hazards effects in a current and changing climate situation, which is obviously a very important topic right now, where we are seeing all of the changes that are happening. I think I can stop it here in terms of presenting myself, and then I'll just start with my presentation, if that is okay. So today I want to talk about the research that we have performed and that are still doing on what I like to call engineered earthen construction, which is the engineering behind using correctly compressed and stabilized earth blocks. So I will define all of these terms in a little bit. But what I wanted to point out is the goal of developing a new system of housing, home building that is at the same time sustainable, affordable, and safe, or as I'm saying here, climate resilient. So I will go through a short introduction, describe motivation, advantages, and challenges in earthen construction. I'll present the results of a feasibility study that we did on using compressed and stabilized earth blocks. Also, our research on modeling using finite elements, ordinary and earthen masonry elements. And then some side projects that are related with the usage of recycled materials and natural materials, for example, reinforcement using natural fibers, usage of recycled soil for production of compressed and stabilized earth blocks, and then some of our results on the wildfire resilience and wildfire emissions that are related to the usage of compressed and stabilized earth blocks. Very briefly, I also will provide some snapshots of ongoing research that we are working on and provide some conclusions. Earthen construction. Earthen construction fundamentally is the usage of soil to build structures. This is a very ancient technique for humans. They've been using it for more than 10,000 years. As you can see in this picture with the orange and the gray, the oranges are the places where homes and buildings constructed using soil can be found, and it is calculated that about 30 to 50% of the world population still lives in earth-based dwellings. Also on the right, you can see some important examples of structures that have been built long ago and are still standing strong after hundreds, if not thousands of years. So it's a very widely used technology, is a very ancient technology, is a very sustainable technology, and as you can see, is also a very safe technology. It exists in very different forms. Historically, we have cob, rammed earth, and adobe, which are different ways of building things with basically the same material. Cob is fundamentally building walls with layers of a slurry made mostly with soil. It's very common in medieval England and Great Britain. Rammed earth is a construction techniques where soil is rammed from both sides into a wall in order to provide more mechanical strength. And an example of that is the Great Wall of China. And then Adobe is probably the one that is most common, at least here in the US, where blocks are made using soil and then pressed by hands or by feet, mixed with straws or other material to provide additional resistance, typically dried under the sun, and then used as you would use normal bricks. A more modern twist on this ancient technology is the usage of modern earth blocks in the three versions of compressed earth blocks, stabilizer blocks, and compressed and stabilized earth blocks. Compressed air blocks fundamentally is soil that is mechanically compressed into the form of a block, and this process increases the mechanical strength of the brick. Stabilizer blocks is when chemical stabilizers are added to the mix in order to provide additional resilience and durability to weathering effects, particularly water. And then compressed and stabilizer blocks is when you are using the two technologies together to have a stronger brick through mechanical compression and a more durable brick through the addition of these chemical stabilizers, which are typically cement or lime. And so our research is focused on these compressed and stabilized earth blocks, which are, in our opinion, the place where modern engineering can be best used to improve not only the material, but also how this material is used. So why are we looking at this ancient technology and then trying to make it modern? But there is two different types of needs. On one side is the need for affordable and sustainable housing. In the US alone, we have a shortage of 0.4, now I think is closer to 0.5 million of houses per year. And an accumulated shortage, this data is a little bit old, but it's definitely more than 5 million houses now. Also, we have a problem with the skilled labor. People that are building in the construction industry, there is not enough people to cover all of the jobs that are available. And we have been becoming more and more dependent on construction material that is coming from other nations, which has a lot of additional problems we have seen during the COVID pandemic, the problem with the supply chains, the timber materials went up more than 100% in cost. This was a huge issue. We are now looking at a situation, political situations where tariffs could again increase prices of the material. All of that has a lot of chain effect on the industry capability to provide homes and houses to people who are in need. There are also a lot of issues with energy consumption and pollution. Typically, the homes that we are building now are not particularly sustainable. And if we look beyond just the United States, it is expected that in the next 50 to 80 years, we will have to build about 2 billion new homes to account for the increase in population and for the improvement in standard of living of people. And that's a huge number of houses. And if we keep doing it the way that we are doing it now, our goal of net zero is just going bye-bye because there is no way of getting there with the techniques that we are using currently. If you add on top of that, that the people that are most suffering for this lack of housing are already those that are low income and typically disadvantaged, then we have a moral imperative of finding a solution that really can address all of these issues. There is also an interest from an engineering point of view. The material that we are investigating is very different from ordinary masonry. So you have a different mechanical behavior, you have lack of standardization. The existing numerical models don't work particularly well for this type of construction, so we need to actually come up with something new in order to be able to perform the same type of engineering analysis that we typically do for other type of constructions. And overall, there is a very limited understanding of performance and reliability of these structures done with new materials, which also has an effect on making more difficult things like permitting and getting these houses built at scale in a way that they can actually make a difference in the home building market. So it's a very interesting problem with a very important and relevant impact on quality of living for people. So another reason that we are looking at this material is that it has a lot of potential advantages if used at scale. First of all, the material is very affordable and locally appropriate and available. You can fundamentally find soil that is appropriate, maybe with some additional modification in the stabilization in order to be used for construction. And here on the right side of this slide, you see the triangle classification of soils from the US Department of Agriculture. And you can see the red line that fundamentally includes the soil compositions that are optimal, that could be used without any modification for construction. And then this dashed line, the yellow line, indicates how you can actually expand the composition that can be used with the appropriate stabilization. As a result, unless you are building exactly on the delta of big rivers like the Mississippi or the Sacramento River, where the soil typically is too rich on expansive clay that are with high content of organic material, every other place can use the soil that are typically available and with very minimal modification, use it for building. So that makes it extremely affordable because it's there and all you need is fundamentally a shovel to use it. Also, earthen construction naturally is resistant to a lot of the problems that typically we have with our timber homes. Mold, fungi, rot, pests, insects like termites and fire, they do not damage soil differently from wood and other organic material. So you have this additional advantage. Also, it is a healthy and natural material. It has two great advantages. One, it doesn't produce volatile organic compounds, which is a very important aspect, particularly for chemically sensitive people. And then it is a breathable material. Fundamentally, when the indoor environment is too dry, it releases humidity that has kept inside in order to make it again in a range of humidity that is between 40 and 60%, which is the optimal humidity for human health. And vice versa, if the environment internally is too humid, it sucks out this extra humidity, putting it into the wall again, and thus again keeps the humidity naturally within that optimal range without the extreme usage of AC and other ways of doing that. It is also eco-efficient and sustainable. And it has advantages both in terms of operational energy, heating and cooling, depending on the climate where you're building. By using the thermal mass of these walls, you can obtain savings in terms of heating and cooling between 30 and 70% when compared with an equivalent wooden home. And it has a smaller embodied energy than other conventional masonry materials because it doesn't require heating for the production of the product. Everything is done with the mechanical energy, and thus the embodied carbon, when compared with the concrete blocks or other common bricks, is about 1 order of magnitude smaller. Now, another component of that is that it has a good hazard resistance. We have investigated the performance of these materials for hurricanes, for tornadoes, for seismic, and more recently for wildfires, which I will discuss a little bit later. But with the appropriate design techniques, you can have homes that are extremely resistant to all of these different hazards. There are also challenges. There are some technical challenges. The first issue is we are using now a natural material and not an industrial material, which naturally produces a higher variability in the mechanical properties. And so if you have a concrete block that typically has a coefficient of variation in the strength that is only of the order of 5%, you can expect a much larger coefficient of variation in the same property for the earth blocks. Also, by nature, it has some issues with the wet climates. You can see here a test that was done representing the equivalent of 20 years of natural climatic conditions, where there is some damage that is at the bottom of the wall due to the capillarity action of water that is coming up from soil and then down depending on the humidity outside. So it also, this requires a particular attention to detailing in order to avoid the negative effect of damage from weathering effects. It is typically a brittle material. This is something that is shared with any cementitious type of composites. If you look at concrete, stone, and even bricks, they all are brittle. So what does brittle mean? It means that once the material reaches its peak strength, it has an immediate reduction of the strength, and so it breaks very rapidly. If you want to visualize it, it's the difference between a piece of chalk and a metal pin. You can bend many times the metal pin before it breaks, but if you try to bend the chalk, maybe you have to exert a higher strength, but then it breaks immediately and you cannot just bring it together. So that's what brittle means. It's also labor intensive. This is shared with all masonry technologies. And these are all technical problems that with ingenuity and modern engineering knowledge can be actually addressed. The big problem is more a cultural type of problem, is the widespread perception of earth construction as a substandard choice. And this is really related to the fact that historically, non-engineered earthen structure have performed poorly, particularly under seismic actions. However, the problem there is not really the material itself, because historically, when other modern material like reinforced concrete or steel have been used without proper engineering of the details and the construction, they also have been performing very poorly. Just consider what happened in other earthquakes in Turkey or in other places where the structures that failed were mostly reinforced concrete structures, which were not well designed for seismic. Another example is Haiti, where again, most of the structures were reinforced concrete and they simply failed like pancakes because they were not designed correctly for seismic loads. So if you use a material incorrectly, no matter what that material is, it will perform poorly. I actually am pretty sure that earthen construction, when used correctly, will perform as safely as other modern materials. So when we are talking about compressed and stabilized earth blocks, how do they look like and how we make them? Here I'm showing you a video of our first Simvaran machine that we built in our lab with some of my students that are very energetically producing some of our blocks. And as you can see, it's a little bit of a laborious process with this hand-held machine. That's how the bricks come out, and you can actually use molds to give all of the different shapes that are shown below. So we can make very varied shapes of bricks. Now we are not using that machine any longer. We were able to produce 30 to 40 blocks per hour with that machine, and the students weren't particularly happy because of the exertion that was connected with it. We actually bought an Auram press. I think it's an Auram 4000 press that we bought. Is a hydraulic machine that produces about 400 blocks per hour, much less work. All you need to do is load the soil on the machine, and then it's carried inside, and the machine spits out the blocks, and then you move the blocks. Students much happier to work with that because much less work and many more blocks in a very much shorter time. So there are actually machines that are even bigger than that. When you want to build an entire house, you can have machines that produce up to 1,000 blocks per hour. We didn't need it for our lab, but that's probably the direction to go. Our first investigation was to understand if using this material is feasible. And for feasible, we really need to look at all of the different aspects of what feasible means. In particular, we identified the three major components. On one side, we want feasibility for structural resilience. Do we make homes and buildings that are strong enough with this material? A second is architectural feasibility. Do we make homes that are pleasant enough that people want to live in these homes? Because otherwise, doesn't matter. You can make the best home, but if no one wants it, no one wants it. And then the third one is economic feasibility. So we were doing an investigation in the US Gulf Coast region. After Katrina, there were more than 400,000 people displaced in need of a permanent home, typically living in mobile homes, which are extremely dangerous for flood and wind, so not something you want to keep people for a long time in. So there was a need for affordable hurricane resistance housing, and we were close to the Mississippi River. Now, if you remember at the beginning, I talked about how bad the soil in the delta of the rivers can be for this type of construction. So we have poor soil quality, typically. We have a hot and wet climate, which we have also said that that's not that good for our material. We have high wind loads, so that's a big load that is applied to our structure. We need to make it safe. And we need to make it so that it's affordable, because the people that do not have homes are the ones that couldn't afford the home. So we needed to have something that is not more expensive than a typical wooden house. We started by investigating the characterization and characterizing the soil around the river. We found that as long as you move at least a couple of miles away from the river, you never are in the optimal region where you can just use the material and make a block, but with some additional chemical stabilizers, some amount of cement, we are in that suboptimal region that can be still used. And then we started investigating the mechanical properties, and we are interested in several different elements. Obviously, compressive strength, modulus of rupture, which is a measure of the tensile and the brittleness of the material. And then we are also interested in two different compressive strength. Due to the nature of this material, where the clay is able to absorb and release humidity, the mechanical properties are highly dependent on the amount of water that is trapped inside the material. And so we wanted both the dry mechanical strength and the wet mechanical strength because they are both connected with different level of performance. As you can see, we used our soil, and then we started adding amount of cement. This 3, 6, 9, and 12 indicates the percentage in weight of solids of cement that we have added to our soil. And we have a minimum requirement for the dry compressive strength and the modulus of rupture that are coming from the New Mexico Administrative Code, which is the only standard or code available that explicitly guides engineers and architects on how to build compressed and stabilized earth block homes, as well as adobe and other earthen construction. And so we needed a minimum strength of under dry conditions of 2 megapascal. You can see how the specimens breaks after the compression strength on the right side of these, on the right figure in this slide. And then we needed a 0.35 megapascal modulus of rupture, which is obtained through the flexure test that is shown on the left side of this figure. So in order to reach these requirements, we needed at least a 6% addition of cement. But then when we started looking at the wet compressive strength, which needs to be above 1.5 megapascal to ensure proper durability of the material, we had to increase our amount of cement to 9 and 12%. And so these two levels are the one that we used for our further investigation of the mechanical properties of the entire structure, not only of the components. The other issue that we had with the wet and the humid climate is to ensure the durability. And so what we did was a test. We built a small wall outside of LSU, and we left it there during the summer for about 6 months to see what was happening to the wall. Now, 6 months may seem a short time, but during that period, we had two tropical storms. So quite a lot of rain, quite a lot of loads. The additional thing we did was to cover half of the wall with a soil cement mix with similar composition as the material that we used for the blocks. And then we looked at what was happening on the two different sides of the block, of the wall. Now you can see in the short video that I showed you how the left side of the wall, the one that was left unprotected, started rapidly degrading. What happened there was that the heavy rain was washing away the mortar. The mortar doesn't have the same compaction properties that were provided to the bricks, and so tends to be washed away more rapidly by the rain that penetrates across the joints. And then when enough mortar was washed away, the top brick fundamentally became a cantilever brick. And then I imagine, even though we had signs saying people don't sit on it, don't touch it, and all of that, probably some students decided to sit on it and broke the block that you see on the top. Anyway, it's not really the type of performance that you want for a wall, even under heavy rain. However, we looked at what happened to this wall. After the 6 months, we demolished the wall by taking brick by brick, and then we tested again the components. And so what we found is that while the unprotected side had a degradation of the strength, the protected side, which even visually looks perfect just by looking at it, not only didn't have any visual damage, but actually the properties kept increasing. The strength, both modulus of rupture and dry compressive strength were significantly higher than the original material. And that is because actually the amount of humidity that was provided by the water kept the cement reacting with the soil, and so that's why the material became stronger and stronger when we retested the material. So a very simple solution to the technical problem of durability is simply having this sacrificial layer that can be done as we did it with the soil and cement, or more traditionally with the lime plaster, which then needs to be fundamentally just repainted on top every 10 years or so, which is a much lower level of maintenance than having to check every year for termites in our wooden walls. Then we looked at the actual strength of these walls. Now here I'm going to get a little bit technical. You can see all of the loads that were considered in analyzing the different walls of the structure. On the right side, in the figure on the right side, that's a very dense figure, but I'll try to go through it to explain what it is. On the horizontal axis, you have the 3-second design wind speed that is used in AC7 to identify the loads that are applied to the houses and buildings that are subjected to tropical storm wind types. The vertical axis reports the mechanical strength of the brick, and the horizontal dashed lines with the indication of M12 and M09 indicate the amount of cement and the corresponding strength for the different blocks. So everything that is below that line is a requirement of strength that is lower than the actual strength for the blocks that were produced with 9% and 12% cement. The vertical lines identify the design wind speed for different towns in southern Louisiana. Houma, for example, is the one that is right there in the middle of the Gulf Coast, where the loads coming from hurricanes are the highest, and New Orleans is pretty close to it. And then you move a little bit more internally. The loads coming from hurricanes tend to diminish as you get far from the coast. And so you have, as you can see, lower requirements for a home that is built in Baton Rouge, and then even lower for one that is in Shreveport and Lafayette, which are other towns in southern Louisiana. Then you have these diagonal lines. Now, these diagonal lines are the one that corresponds to the combination between mechanical strength and the thickness of the wall that is needed to provide enough strength for a given wind speed. So for example, if I look at the red line here, it's at about 2 megapascal, the vertical line for UMA. And that means that we can use a thickness of 305 millimeters, 30 centimeters, that's about 12 inches wall, when using one of our blocks with 12% cement, and that would give us a house that has more than enough strength for the requirements that is corresponding to this wind speed. If we are looking at the one corresponding to the purple line, we could use for the same place a block that is done with 9% cement, but then the thickness should be 35 centimeters, so 14 inches of wall instead of 12 inches of wall. So this is a very simple tool for engineers to identify the strength of the block that is needed, and then given the strength of the block, what is the thickness of the wall that is needed in order to provide a code, in house that satisfied the code requirement in terms of resistance to wind. And then with this information, we started assessing what would be the cost of building these houses. We did our investigation with the two different typical homes that are built in southern Louisiana. The one that I'm showing here is called a shotgun house. We used a prototype of 1,000 square feet so that we had something that was easily comparable with other things. Now, the shotgun is the typical house that is used in towns, in urban environment, where the house is elongated so that the wind can enter from one side and produce fundamentally natural air conditioning just by having the airflow through the entire house. The other type of house that we investigated is called the dog trot, and that is a more rural home where you have an internal cart, and then the air is fundamentally flowing from the internal cart within all of the rooms that are around it. I'm not presenting it here just because of time limitation. I didn't want to present too much stuff, but we did the calculations for both types of homes, and we compared the costs that are coming, these are costs for 2015, so they're not anymore updated. When we did the study was 2015. And we compared the ordinary light frame wooden constructions, ordinary brick construction, concrete block construction, and then ordinary mortared, compressed and stabilized earth blocks, and also a new technology that we were testing, that we have developed, that we called interlocking compressed and stabilized earth blocks, which is also mortarless. So fundamentally, we are using shear keys in the blocks to keep everything together without having to add an additional layer of mortar between the blocks. You can see that when you compare the different costs, the masonry constructions are typically more expensive than light frame wood, even though even the mortar, the compressor stabilizer blocks is more expensive than light frame wood. Although the total increase in cost is, in our calculation, less than 15% overall. And this is with the material being significantly cheaper, but the labor ends up being higher. However, with the interlocking mortarless compressed stabilized earth blocks, we were able to reduce labor almost by 50% in terms of cost. And we ended up with something that is fundamentally the same cost as a light frame wooden construction. So our calculations actually gave us a 5% decrease in cost for the construction of the walls, which was about a 2% decrease in cost overall for the construction of, sorry about that, for the entire house. Again, these are data that are specified for Southern Louisiana and for 2015, so a little bit out of date, but our goal was to develop a technique that would have similar costs as the one of light frame wood, with all of the advantages that are connected with the earthen construction. Now I'm going to switch to another technical problem that we have been addressing. So we were very happy with the results of our feasibility study, but now we wanted to go from, okay, it is feasible, how do we make it actually happen? And there are several different problems that need to be addressed. One of them is in order to design structures beyond just homes, you need to be able to calculate their strength using engineering knowledge. And one of the tools that is used is finite element modeling. But the finite element modeling that are used for ordinary masonry, which are the one that exists in the literature, don't work very well for earthen construction. And I'm going to go through the reasons and explain how we addressed that. The best methodology for modeling the response and the performance of walls made with the masonry elements is the so-called finite element micromodeling approach, where we decompose the different elements of the wall into units and mortar, and then we use different ways of modeling it. What we need to obtain is a final model that is able to account for all of the different types of failures, which are going from tensile cracking of the blocks to tensile cracking of the joint, the slipping of different blocks one on top of the other, diagonal cracking, and then crashing of the masonry. So we need something that is able to identify all of these mechanisms of failure, because any of them could happen. And typically for ordinary masonry, there is an approach that is called the simplified micromodeling, where the blocks are expanded. The mortar joint is represented by a zero thickness model that is called the interface element. And so you get fundamentally that the interface element accounts for joint slipping and part of the cracking for tensile effects, while the blocks typically account for the masonry crashing or the direct tensile cracking. Now, this is the model that fundamentally assumes that everything that is breaking is happening in the interface, which is a reasonable assumption to be made for ordinary masonry, where the blocks are typically very strong and the mortar is weaker. But for earthen construction, we have that the mortar is very similar. It's done with the same material as the blocks. So this assumption that allows the use of a simplified micromodel simply is not satisfied. And so we came up with a detailed micromodel where we actually model explicitly also the layer of mortar. So what happens? For the interface and the mortar, we needed to develop a constitutive model that is still accounting for the different mechanisms. I won't enter too much into the details of this, but fundamentally the blue line is the one that models the cracking because of tension and the cracking because of shear slipping, while the red line is the one where compression and cracking because of combination of shear and compression is controlling the mechanism of rupture of our wall. So with this new model and with the new approach of modeling, we went ahead and we started seeing how it would perform first with ordinary masonry. These are experiments that are available in the literature for ordinary masonry. And we modeled it with our different techniques. You can see the blue line is the results of our numerical simulation and how it compares with the black lines, which are the experimental results. Now, in addition to having this very nice correspondence between the horizontal force, horizontal displacement globally for our walls, we also had a very nice matching of the cracking pattern that our numerical model had with the cracking pattern that was observed experimentally. If you look at the open spaces in these red figure here, those are where the cracks form and where there is separation of the blocks. And then you can compare it with the dark lines in the experimental results here. And you can see that fundamentally we are capturing not only the global behavior, but also the local behavior and the formation of cracking. So we found that these results were pretty good with all of the different models, including the simplified and the detailed micro model that we developed. You can see, again, a comparison of numerical results with experimental results when you change the level of compression that is applied on these walls. We are still doing pretty well with both simplified models and detailed models. So this fundamentally told us doing a detailed micro model, which is computationally more expensive for ordinary masonry, doesn't really make sense because the simplified models are already pretty good. But then we did the same exercise with compressed and stabilized wallets. Again, you can see on the right side the end results of the experimental testing. The black lines here correspond to the experimental results, and then the other colored lines are the results that are coming from the simplified micro model, which are not good. We are overestimating up to 200% the value of the load that this wall can take when loaded diagonally. So here is when our new model actually starts really doing well. You can see this yellowish line is our new model, which is pretty good in capturing not only the peak strength of the wallet, but also this lighter color here is where formation of cracks is happening. And so our model is actually able to capture the cracking going through the bricks, which is fundamentally physically impossible to capture with the simplified micromodels. And that is the reason that the simplified micromodels are not able to capture the real strength of these walls. So fundamentally, what we have accomplished is that now we can use modern finite element technology in order to predict the performance of walls made with our material, which is a fundamental ingredient in order to be able to use it in an engineering sense. Another study we did was to address one of the other problems that I was describing at the beginning, which is the brittleness of these materials. Again, we started this investigation in southern Louisiana, where there is a big production of sugar with the sugar cane. And big production of sugar also produces a lot of extra material that needs to be disposed of. And these comes in the form of sugarcane bagasse fibers and sugarcane bagasse ash. For this particular study, we investigated the uses of the fibers directly in the block in order to improve the brittle behavior. We know from the usage of other type of fibers that they improve the post-peak behavior of our material, which fundamentally gives the ductile behavior that I discussed at the beginning. If you're thinking about a pin made of metal that you can deflect, deform in a way that you change completely the shape, the material still doesn't break. That's what we want to obtain here. And so we have these 28 million of tons that are produced in Florida, Louisiana, and Texas of sugar cane, which lead to more than 9 million of tons of sugarcane bagasse fibers that need to be disposed every year. And we are trying to find a use for that. And so what we did, we considered blocks with three different amounts of cement, 0, 6, and 12%, again, expressed as weight of total solids. And with three different levels of sugarcane bagasse fibers, 0%, 0.5%, and 1%. This amount is expressed in volume of the material. And what we did was performing a flexure test and compression test to identify how we modify the ductility, the post-peak performance of these materials. What we found, not surprising, is that increasing the amount of fibers produces a less rapid deterioration of strength after the post-peak, with only minimal changes in the actual peak strength. If you look at the same amount of cement for a fixed amount of cement and a change in fibers, what we get is that there is a delay in the peak point, and the peak value typically doesn't change a lot. With the increase in amount of cement, what we found is a general increase in strength and the same type of behavior in terms of fibers. So fundamentally, we are improving the performance of the material post-peak in terms of brittleness. And this is particularly evident when testing the material in compression. You can see here the lines corresponding to no fibers are the black lines, the one corresponding to 0.5% fibers are the one with the red lines, and then the purple lines are the one with 1% fiber. This is again done for a fixed amount of cement. When you increase the cement, you increase the peak. When you increase the fibers, the peak typically remains the same. It's just moved more for larger displacements, and it allows also a maintenance of the peak strength for a much wider range of displacements, which is exactly the type of ductile behavior that we wanted to achieve. So the usage of natural fibers is a positive addition for improving the overall ductility of this material, which is useful for both wind loads and seismic loads. A thing we were worried about was the effect of fibers on the durability of the material. The reason being having a lot of fibers inside the material can suck even more water inside, and we were worried about the production of micro cracking inside the materials. Now, we observed a little bit of increase in loss of mass for the increase in fibers. However, the best way to address that is the increase in amount of cement, and we found that with zero cement, fundamentally, it doesn't matter how much fiber you're using, the material disintegrates after 12 cycles of wetting and drying and scratching the surface. To describe the test, fundamentally, what we are doing is we wet the material by submerging it in water for 5 hours. Then we use a metal brush to see how much material gets removed after each of these cycles. Then we dry the material. Once it's dry, we go through that process for 12 times. And then we measure the total loss of mass from the different materials. With the 0%, all of the material was always lost after the 12 cycles. With 6%, the loss in mass was quite significant, about 15% in average. With a 12% cement, the loss in mass was well within the limits that are considered acceptable. So there is some attention that needs to be done with the addition of fibers in this material, and that has to be balanced because fundamentally, I wouldn't generally recommend the usage of a 12% cement in these materials, except the material, the base material that we were using in southern Louisiana was already a low quality soil and with the high requirement in strength. Then we investigated the fire resilience of our material. So I'm switching again a topic to show all of the different things that are needed to really evaluate the quality of the material and the feasibility in usage. But this was something quite obvious to me, that soil is the only thing that remains after fires. It doesn't burn. So here you can see the comparison of our earth block and a wood block of a 2x4 typically used for construction of homes. In our earth block, all you can see is a little bit change of color, and obviously the wood is completely charred. On the bottom right side, you can see the comparison of our block as it is, and then a block that was subjected to 7 hours of flames at the 1800 Fahrenheit, about 100. Actually, it was 1000 Celsius, about 1800 Fahrenheit, 1820 to be more precise. So fundamentally, again, all you see is a changing color of the block, but there is no real degradation of the material. And that is after 7 hours in a furnace at a very high temperature. So we wanted to have a little bit more information on what is happening, and we did a complete study on the performance of the material. We used soil collected from Paradise, California, after the campfire. You may be aware of the fact that the town of Paradise was fundamentally completely destroyed during the 2018 campfire fire. And so we wanted to investigate that particular soil to provide an option for a more resilient type of construction in a very high fire hazard zone that was just destroyed by fire. Here the details on the material. We used a 9% Portland cement amount in weight of dry natural soil. And we did the investigation of all of the physical properties of the soil in terms of particle analysis, Attenberg limits that are fundamentally the amount of water where the soil starts changing physical composition. We did the soil compaction test to find the optimum moisture content that would be needed to produce the maximum compaction of the material that is optimal for our blocks. We were still using our manual Simbaram, the blue machine that I showed you at the beginning, which requires a lot of work. So we did only 60 specimens for this investigation. These specimens were divided into 6 groups of 10 specimens. Some that were left at room temperature, and then others that were tested under 200 Celsius, 400 Celsius, 600 Celsius, 800 Celsius, and the 1000 Celsius that I indicated before, the 1800 Fahrenheit, which is a very high value of temperature for a wildfire. And so we, after eating the materials for several hours, we tested them under a 3-point flexure test to find the modulus of rupture. And then the 2 parts of each of the specimens were trimmed to produce the specimen for compression test that were tested both with dry compression and wet compression. These are the blocks and their the visual inspection of the blocks after the eating. You can see the color changes from light brown to a reddish color. After the flexure test, if you look at the inside, you see this propagation of the red from the outside toward the inside until you reach the complete red of the 1000 Celsius. And this was the first indication of what we were kind of expecting. These blocks are transforming at the different temperature from earth blocks to normal fired clay bricks. What we found is that there is a small reduction in terms of modulus of rupture for different temperature. There are 2 important things here. One is even at 1000 Celsius, we are still above the requirements for the New Mexico administrative code, the building code in New Mexico, which means that the structure is still safe under the fire to be inhabited. The other thing is that we identified the reason for this reduction of the modulus of rupture, and this was really the formation of microfracture due to the presence of cement. And so actually our conclusion was that we used too much cement. We could have had a better performance by using a little bit cement than what we used, which I guess is good for optimizing these blocks in the future. But from the modulus of rupture, we have this slight decrease in the performance, which is still above the minimum requirement for the New Mexico administrative code. In terms of dry and wet compression, there is a small reduction in compressive strength under dry conditions, which is actually statistically insignificant. So we cannot really state there is a reduction because statistically speaking, the difference is so small. So fundamentally, from a practical point of view, there is a maintenance of the dry compressive strength of the material across all of the temperatures that we have investigated. However, what was interesting is that under wet compressive strength, we actually had a very significant increase in strength, almost a 5-fold increase in strength. And with in hindsight, that was to be expected because we were now cooking our unfired clay bricks into fired clay bricks, which are very resistant to wet cycles and do not really change strength between wet and dry conditions. So an important result is that fundamentally, even if things go wrong and the house gets burned, the walls will be still standing and they will be still safe to be used. Another investigation that we did was to understand the wildfire emissions that are coming when things go wrong and the house burns. Now, our goal is to actually have houses that do not burn at all, but we wanted to understand what happens even in the worst case scenario. So we came up with a framework to assess the emissions estimated in terms of CO2 equivalent, and then eventually combine it with a life cycle assessment for understanding the greenhouse warming power associated with our construction versus a normal wooden construction. We focused only in the first part of our research on the emissions only, because that was already a big contribution to knowledge. And we took as an example a pre-designed structure that was used for the reconstruction in Paradise using light frame wooden construction. But then we also designed it in different versions with respecting Chapter 7A requirements without respecting Chapter 7A requirements, and then building it with earth block materials. We did an investigation of all of the materials that are included, and then for each of these materials, we did test to evaluate the emissions per unit mass of material. We found out that actually with the interlocking construction, we can be cheaper than a wooden construction that is compliant with Chapter 7A. The LFWCA corresponds to light framed wooden construction that is non-compliant, so older structures before 2008. The LFWCB is the same wooden construction but compliant with Chapter 7A. Chapter 7A, if you are not aware, is the chapter that indicates requirements for construction of homes and buildings in the wild and urban interface to provide additional resistance to wildfire. So our earth block construction is more resilient to wildfires and cheaper than a compliant structure. We did some additional assumption, particularly in the life cycle part assessment. We took results that were already available in the literature. We didn't do our own calculations. Also, we could not add the effect of paints and of gypsum boards and drywalls because at that time those data were not available, and so we just removed that from our calculations of emissions. And we did our evaluations, calculating how much CO2, methane, formaldehyde, and other materials are produced when burning all of the different types of materials that are used in the construction. And we ended up with an estimate per unit area of emissions in terms of kilograms of CO2 equivalents for the light frame wooden construction, for when it is non-compliant and compliant, and then for the earth block construction. So just to summarize, what we are calculating is how much emissions in terms of equivalent greenhouse gases are coming out, assuming that the house burns completely. And you can see that per unit area, the effect in terms of emissions coming from the earth block construction is about a third of the total emissions that is coming with the light frame wooden construction, which is quite obvious because in a light frame wooden constructions, everything burns. While in earth block constructions, almost everything is in the content, coming from the content of the building and not from the structure itself. So to give it graphically, we took from the literature the estimates in terms of embodied energy from the original construction. And you can see that fundamentally earth block construction is very similar to the wooden construction in terms of the initial embodied energy, which is already a big advantage when compared with the concrete or brick homes, which have an order of magnitude higher in terms of embodied energy. But then when you compare it in terms of total emissions, including the effect of wildfire burn, now you have a total emissions that is significantly lower than the one coming from a wooden construction. It's about a third of it. Which has a huge impact on air quality and global warming coming from burning of built environment in the construction of homes. So it's something that definitely should be accounted for when deciding what materials to use in the construction. Another investigation that we did, again, to understand our sustainability was the use of recycled soil for compressed and stabilized earth blocks. The idea is we want to have the complete life cycle from cradle to grave, and we don't want to have a lot of blocks that are just put into a landfill after the construction. So can we reuse this material? And there are two different ways of doing it. One is putting it back into nature, which we are investigating, and then using it for making pristine blocks using the same soil without having to extract additional soil. Here, what we started with was natural soil, again, obtained locally with a pretty high amount of cement. Again, in on-site, we would have used less, 12% cement. We made our blocks, which we investigated in the same way we did with the other ones. And then after breaking them, we used the material from the broken soil to fundamentally recycle it by grinding it and then remixing it with the different amount of natural soil and cement to produce new bricks. And the comparison was done in terms of flexural strength and compressive strength. And here you can see that actually what you get is a strength that increases when you use more of recycled soil. The 0% correspond to the original blocks done with only natural soil. Then 25, 50, 75, 100% is the amount of recycled soil that is used to reproduce new blocks. And you can see an increase both in the modulus of rupture and in the dry compressive strength with the increase of the recycled amount of soil in the mix. We did also our durability test. And here we were pleasantly surprised to find out that fundamentally usage of recycled soil has no statistically significant effect on the durability. We have a loss in mass that is overall smaller than 2% at all of the different level of recycled soil. Fundamentally, the outcome of this research is that for construction purposes, you can reuse 100% of the material. It's 100% recyclable, which is a nice thing to have. I think I'm getting close to the end of my time, and so I just wanted to go with a few nuggets from research that is ongoing. One interesting research is the use of earthen material for 3D printing. This is actually our first successful printout that you see in this video. But now with the same machine that I'm showing here and the different auger, we are able to print walls that are 6 feet by 6 feet of dimension, so 6 feet wide, 6 feet high. And the material is fundamentally similar to the material we use for the blocks, with a little bit less gravel in order to have a easier flow. But we fundamentally are at the point where 3D printing of earthen material is a feasible technique that has a lot of potential applications for the future. And then another investigation that we did was that also contributed a lot to funding all of the research on wildfires was the investigation of wildfire-induced air pollution and also techniques for its mitigation. I'm not going to go into the details of the entire framework, but fundamentally in this research, we went from being able to model and forecast wildfires, both at the small scale of building to building and tree to tree propagation, to a large scale with statistical models for assessing the risk at the regional level or at the state level. If, evaluating the emissions coming from both vegetation and urban or suburban fuel, as well as the effect in terms of air quality and the effect on health of both individuals and population. All of this information was fed into the different mitigation strategies which we considered, including management of vegetation, prescribed burns, land use policies, and fireproof or fire resilient construction. And then this information was fed back to our wildfire modeling to see and quantify what the mitigation strategies can do in terms of reducing the negative effect on health of both individuals and population. And so this was a big project that just completed last month, where fireproof construction or fire resilient construction is one of the ingredients of the different mitigation strategies which we can use to reduce the effect of wildfire air pollution on population health. Another project that is ongoing is the development of a facility for testing of entire structures under wildfire conditions. The idea is to put a structure here, and actually we have just built our first specimen, which is an earth block shed of 6 by 9 feet dimension, which hopefully will be able to test between this and next month. And then put flames on at least 3 sides that are directly impinging on the structure in order to evaluate what is happening at the intersection of different components. Chapter 7A and the current standards that are used for construction are typically taking an approach of component or assembly at a time. So you test a wall, you test a window, you test a door, you test a piece of roof, but it's not really giving a lot of indications and guidance on what to do at the connection of different components. Only a test that actually includes the entire structure can holistically assess if what we are doing is fine or not. And this facility that we are building will be the first public facility to do that type of test. And with that, I have just a few conclusions. The first conclusion is that earthen masonry represent a technique that is at the same time affordable, safe, and sustainable, and can be really used for construction of houses and low-rise buildings. these houses, low-rise buildings, 1, 2 stories typically, can be designed to properly perform under different types of loadings, seismic loadings, hurricane loadings, tornado actions, and we will see wildfire. We have developed this finite element detailed micro modeling approach, which has demonstrated has been proved to be accurate in predicting the mechanical behavior of earthen construction. We have used natural fibers to improve the ductility of compressed and stabilized earth blocks. We have seen that compressed and stabilized earth blocks can be used as a fire-resilient construction material. I think I forgot here to add that also the material can be recycled 100% for usage in new constructions. And overall, earthen masonry shows great potential to address two big problems that we are trying to tackle. One is climate change, and the other is equitable economic development. I didn't discuss about good stories of usage of earthen construction across the world, but there are some groups that have been very successful in doing that. And I guess a shout out to Almighty that has been very successful donating a earth block machine to a community in northern Haiti, and spurring from that a company that has built more than 800 houses, several schools and churches, and has been giving stable jobs to more than 120 people for several years. So we can really get multiple benefits from using this type of construction. I always have to conclude with acknowledgments, and there are two different types of acknowledgments here. The economic acknowledgments: without funding, research doesn't happen. And you can see this was funded by UCOP Lab Fees Program, EPRI, the Electric Power Research Institute, National Science Foundation, the Louisiana Board of Regents Economic Development Assistance, the LSU Coastal Sustainability Studio, and the Jeff Cook Charitable Trust. And then collaboration acknowledgements, Dr. Mata and Dr. Engifo Lopez in University of South Carolina, Dr. Holton in LSU at Louisiana State University, and then my students and postdocs, Dr. Nitin Kumar and Mr. Merab Nodey here at the University of California. Also, without good students and postdocs, no research happens. So it's not just my work, it's work of the entire team, and I feel like it's important to acknowledge their work. I think with this, I'm going to stop. Thank you very much for your attention, and I'll be happy to respond to any question you may have. And I know this is a recorded one, so I put there my contact information if you want to reach out directly to me. The best way of reaching me is my email, mbarbato@ucdavis.edu. And if you are curious and you want to know more about other aspects of my work, there is also the link to my research lab, where you can see all of the work on earthen construction, plus my work on assessing hazard effects due to climate change and other risks associated with a changing climate. Thank you very much.
Thank you so much, Michele. I know that you need to go. You have a class coming up.
Yes.
Because I had definitely some comments and some questions also for you, but I think if you have to go, then we'll
I can stay for about another 6 minutes. So if you want to have very short questions, I can respond to them for about 6 more minutes.
Sounds good. There's two specific aspects that I would be very interested in. One is you mentioned having done the test with cement, I think it would be very interesting to know how the stabilized compressed earth blocks would do with lime as a stabilizer. And also, I'm wondering, like as you were saying at the beginning, an earthen material is able to breathe, it's able to regulate humidity. I'm wondering, putting specific amounts of cement in it, how much does that hinder that ability to some extent? How much does it seal the blocks in such? And then there's another really interesting aspect, I think, that you mentioned, which is the recycling. And as far as I understand, the way cement works is that once it sets, it's done. Whereas clay, you can re-wet it and then reuse it again. So I think it's very interesting the fact that you're reusing these blocks. Again, does cement even have the same property that it had in the first place? And if such, it really shows, it says a lot about the durability of the material as such.
Yes, so let's take one question at a time. The first is lime. We have started using lime more recently, and our preliminary results fundamentally tells us that the lime performs very well in terms of maintaining the durability of the blocks. Which means that we need to get the strength really from the clay binder, not from the cement. In several parts of my research, I said we probably use too much cement. And in fact, we have shied away from the 12% amount of cement now. We have found that with the soils that we have locally here in California, a 6% cement is typically more than sufficient for both strength and durability. And with that level of cement, kind of responding already to the second question, typically the amount of cement is not sufficient to seal it. So fundamentally, you want to remain below or at most at 6% for several reasons. One is it's more sustainable. Two, it really allows clay to work as a binder. And three, it doesn't seal it and doesn't lose too much of the breathability of the material. If you want to increase the mechanical strength, the best approach to use is actually to increase the pressure that is used in the compression of the material instead of using cement, because if you start using 12% cement, now you're talking really about fundamentally a CMU. A CMU typically has a 15% cement. So can you still say, oh, we are so sustainable when you are reducing only by 3% the amount of cement? I find it a little bit more difficult to justify. But this is something that we have learned just by working with the material, because there wasn't any guidance. And so the way we started was, what is that people are familiar with? Cement. How can we make it so that it doesn't sound like a crazy idea to them? Put a lot of cement. Now that we have more experience and we have figured out that we really don't need that cement. And actually, if you are doing something with wildfires, cement is bad because it breaks around 400 Celsius, while soil goes up to 1200 Celsius before it starts classifying. Then it just makes sense to use as little cement as possible and increase the strength with the extra compression. So I guess this responds also to your second question. With the 12% cement that we used in Louisiana, we actually saw a reduction in the capability of breathability. It wasn't reduced to zero, but there was a significant difference. So now we are actually trying to measure that more precisely to know what is happening with the different amount of cement and how that compares when you're using lime or a mix of lime and cement, which is also a possibility where you can use very little cement, like 1 or 2%, and then 1 or 2% lime up to 3% lime, and get the best of the two worlds without losing any of the properties. Then you had a third question on the recyclability of the material. So the cement, as you said, was already reacted on that material. So what we had to do was rendering it into granular form. We had to grind it so that fundamentally had the same type of granulometry as the original soil in order to be reused. And so in that case, what you have is that cement is not very different from a little rock, and that's why it was working so well in the slides that I showed you. Fundamentally, what is happening is you are increasing the sand amount, and so it's more sandy original natural soil, and that gives the increase in strength. Exactly 12:40. Now
Excellent. No, thank you so much. Really, really appreciate
I hope
it.
we can talk again, and maybe if your students have any question, just have them send it to me or send them to me by email, and I'll try to address them as I know and as I can.
Sounds
And
great.
was a pleasure. Now I need to run.
Okay, pleasure.